Hello, my name is Abigail Barenblit. I am a data analyst at NASA Goddard and the University of Maryland. I am also in the fifth year of my PhD at the University of Maryland. I work with Dr. Lola Fatagimbo and Dr. Laura Duncanson. This work bridges my day job at NASA Goddard with my dissertation work. I am using Jedi LiDAR to understand structure in forests, particularly as it pertains to protected areas in West Africa and how those dynamics shift between protected areas and not protected counterparts. In recent years, we've become more and more aware of the fact that biodiversity worldwide is under threat. And this is especially true in Afrotropical regions. In this area, forests are under stress due to deforestation, wildfires, pests, and storms, as well as anthropogenic drivers such as urbanization, resource exploration, and agriculture. Thankfully, we have a really amazing tool in our tool belts in the form of protected areas. These regions that may fall under national or international governance are viewed as being critical for preserving hotspots of biodiversity. They currently cover about 16% of the Earth's terrestrial surface, and numerous studies have indicated that protected areas can have positive spillover effects on areas outside of the protection zone. Currently, the UN has this goal of 30 by 30, where 30% of the Earth's terrestrial surface will be protected by the year 2030. And in order to establish more protected areas, we want to better understand how our current protected areas work and how to better identify critical spots for conservation efforts. In accordance with this goal, there have been global studies of protected areas, including this paper performed by Laura Duncanson in 2023, looking at the effectiveness of global protected areas for climate change mitigation. This paper was looking at above ground biomass and other indicators of carbon storage to determine if protected areas conserved more carbon than not protected counterfactuals. What they found was this positive difference across the 6 continents of study, where protected areas were storing more carbon than their not protected counterfactuals. This also indicates that other forest structure beyond carbon may be negatively affected by the absence of a protected status. When we look at the results of this paper over Africa, what we notice is that while there was a positive percent difference between protected and not protected areas, where protected areas were storing more carbon, the magnitude of this difference was lower than what was expected based on what was determined in other continents. This may be because protected areas in Africa experience higher rates of disturbance. However, there could be a lot more to this story here. And so we wanted to dive into the African continent specifically, and more specifically, West Africa, to better understand the dynamics of what is actually happening in these protected areas. To delve into these dynamics further, I wanted to look at forest structural dynamics and use other capabilities of Jedi LiDAR to understand what is happening beneath the canopy in protected areas and if that differs between protected and not protected areas. While this video is not taken in West Africa, it is a good demonstration of what forest structure looks like and what I mean by forest structural diversity. It's the vegetation density between the canopy and the forest floor. And we can get metrics of this from Jedi LiDAR. To look at this information, I subset a region to countries along the coast of West Africa. So we looked from Senegal all the way down to the Democratic Republic of the Congo. To give you a visual of what that 16% coverage of protected areas look like, I've indicated our protected areas of interest in green on this map. Because we're looking at such a large region, this does mean that we are also looking at several different land cover types. We're looking at forest, woodland, scrubland, mangrove, flooded forest, agriculture, among others. Now from this map, you can see that we already understand where our protected areas are, which means that our next step is to establish a sample of not protected areas. To do that, we want to do our best to compare apples to apples. So we take a protected area, so for example, the Rio Cashew mangroves, and we want to determine what characteristics define this area. We use a bunch of different characteristics, including land cover type, population density, population count, mean temperature, mean precipitation, elevation, slope, distance to cities. These all are biotic and abiotic characteristics of this region. And we look at what the data availability is to use a baseline year. In the case of this study, we used the year 2000 as a baseline year, a year before different patterns of degradation emerge, before some urban development emerges. We then take all of the rasters of this information and we stack them together. We use this information to create 1 kilometer samples over these regions. And using statistical matching, we identify not protected areas that have similar, if not equivalent, characteristics. So that essentially we are looking at areas that have similar land cover types, similar accessibility, so that we can say that a protected area is statistically similar to a not protected match. In order to perform this analysis, I was able to utilize a collaboration between NASA and ESA, which is the MAP. This is a platform for co-located data sets and tools that improves the use of large data sets required for these types of analysis. This includes the biomass data set that will be available on the MAP, NISAR, and JEDI. This is a collaborative cloud computing software. If you haven't seen the platform before, it looks like this from the ESA side of things. The NASA side looks a little bit different. And I've been working with the developers of this platform to improve its accessibility, its usability. This does mean that because I started working with it a couple of years ago, I was one of the guinea pigs on the project, but the developers of the MAP platform have been incredible to work with to get this project moving forward. Now, to return to the sensor I'm using, JEDI LiDAR is a sampling mission. This means that rather than having full coverage, we are getting 25-meter samples across the surface of the Earth. And despite not being full coverage, because it is making all of these returns across the globe, we're able to build information about patterns that we're seeing across the surface of the Earth. And this is an example of what height looks like from the JEDI sensor. When we look at the data that we get from the JEDI sensor, this is a figure demonstrating what the returns of the laser look like. And essentially, the information that we're getting is the returns of energy that can tell us information about vegetation between the top of the canopy and the forest floor. And for the purposes of this talk, I've used a couple of different metrics that we get from JEDI. We have height as measured by RH98, which is the relative height at the 98th percent return. And there's also a derived metric for foliage height diversity that from now on, I'm just going to be referring to as structural diversity. On my end, when I'm looking at JEDI data, it looks a bit something like this. You're seeing the returns of the JEDI data as marked by these footprints. And I'm able to take all the data associated with these footprints and extract that information over all of the protected areas and the not protected counterfactuals. From this information, we can start building patterns of how those compare across the West African region. If we want to simplify the patterns that we're seeing, we can look at these percent differences the way the global paper did. On the left, we have our different countries, and these graphs are showing what the percent difference is. A positive percent difference is indicating green, negative is indicated in gray. These are the percent differences we're seeing between all 16 countries of interest based on height and structural diversity. But I'm not going to go into all of them. What I want to point out is these two countries in particular, Ghana and Republic of the Congo. As you can see in both of these graphs, Ghana has the highest positive percent difference between protected and not protected areas, whereas Republic of the Congo has some of the lowest values of percent difference. And the question arises, what is this actually saying about the protected areas? Is this saying that Ghana is having a higher positive impact than Republic of the Congo, or is there more to the story? And my theory is that there is more to the story, which brings us back to some of the foundations of conservation ecology. When we are thinking about protected areas, we can have intact forest and degraded forest that we're working with. If we're working with an intact forest, they already tend to have higher trees and higher structural diversity. When we look at degraded forests, these values tend to be lower. And so there are a few different scenarios that we'll see. When we put in a protected area over intact forest, we are hoping to see that these values remain static. So essentially, a tall, structurally diverse forest stays tall and structurally diverse. In a degraded forest, we want to see that shorter forests are becoming taller and are becoming more structurally diverse. Another scenario that we want to keep an eye out for is if we don't see these patterns. So, for example, if we see that a protected, tall, and structurally diverse forest becomes short and less structurally diverse due to cutting or degradation, or if a degraded forest remains static and we don't see a shift towards taller, more structurally diverse forest. Now, if we want to understand which of these scenarios we are looking at, we also need to understand more about what's happening on a countrywide level. So if we look at patterns of deforestation in Republic of the Congo, we can get statistics from Global Forest Watch that indicate that between 2000 and 2024, Republic of the Congo only experienced 4.4% loss of forest. When we compare that to Ghana, however, we see that there was a 25% loss of forest in this time. This is indicating that Ghana is experiencing more deforestation in this time period, and this may explain some of the patterns that we are about to see. In these graphs, our not protected areas are indicated in purple, our protected areas are indicated in blue, and areas of green are highlighting an increase of values between protected and not protected areas. When we look at the Republic of the Congo, what we're seeing is a similar distribution between protected and not protected areas. Whether an area is protected or not, it tends to be tall and structurally diverse. And this is an indicator of what we see from Global Forest Watch, that Republic of the Congo currently experiences low deforestation rates. In Ghana, we see that protected areas tend to be taller and more structurally diverse than not protected areas. So when we look at these two countries, we have two different positive takeaways. One is that in a country that is highly forested, protected areas and not protected areas look similar because across the country, we see tall and structurally diverse forest. In a country experiencing deforestation like Ghana, the takeaway here is that protected areas are allowing for taller, more structurally diverse forests and are having a positive impact on those metrics of forest health. For Republic of the Congo, when we try to break this pattern down by land cover type, by protected area type, we see the patterns are similar across protected and not protected areas throughout. So for now, I'm going to dig more into Ghana specifically. We can look at the patterns between protected and not protected area broken down by protected area type. This may indicate the governance of a protected area and how enforcement works. It may also give us information about vegetation type. So here on the top, you can see national parks, then followed by Ramsar sites, and then UNESCO biospheres. Ramsar sites are specifically of interest because these are wetland areas. So we would expect these patterns to be different from our other more inland forests. What we see overall is that the magnitude and direction of difference varies by protected area type, and this makes a lot of sense. We're seeing that national parks in particular have a positive impact on structural diversity and height. Ramsar sites have a negative impact on these values. However, because these are wetlands, this is not necessarily a negative message. This isn't necessarily saying these protected areas are ineffective. It's just that the vegetation is different. And so we need to look into this pattern a bit more before we determine anything about the effectiveness about these particular protected areas. We can also break down the pattern by land cover type. The land cover layer that I used was the GLAD Global Land Cover Data Set, and these are the three most common land cover types indicated in Ghana from that data set. We have dense short vegetation, trees 3 to 10 meters, and trees 11 to 20 meters. What's interesting here is that across all of these land cover types, we see that protected areas are taller and more structurally diverse, which again is indicating this positive impact of protected areas in Ghana on these metrics. The takeaways from this project so far are that the magnitude of effect of protected areas on height and diversity varies across country and protection type. This means that we need to do a lot more digging into the different patterns that we're seeing. And context is critical for understanding the patterns of protected area difference across West Africa. Looking at the percent mean is informational, but not enough to determine the positive impacts of a protected area and better inform the construction of new protected areas. So there are more positive patterns to be revealed than through differencing alone. And finally, where I want to take this project is indexing the results to improve the selection of new protected areas to meet the UN's 30 by 30 goal. My hope is that the results of this work, when it is published, are going to be informational for the establishment of new protected areas and for the increasing protection of biodiversity hotspots. With that, I would really love to thank my team, all of whom have been critical for this work. Finally, I hope that you follow this project as I keep working on it. The next step that I want to take with working on protected areas in West Africa is to incorporate more of a direct biodiversity measurement. And so if you would like to collaborate and have access to bird data in any of these protected areas, I am available via email. Please reach out, and I look forward to providing updates to this project in the future.